Hello everyone, my name is Kai Cai. In this talk, I'm going to introduce different types of graph Laplacian matrices and explain how we can use them to connect the dots in different cooperative control problems of multi-agent systems. This is part 2 of the talk. In the previous part 1, we have introduced the standard type Laplacian matrices, which plays a key role in establish multi-agent rendezvous or consensus. In this part 2, we are going to introduce the second type, complex Laplacian matrices, and we will see how it can be used to establish what's called a similar formation control behavior. So let's get into it. Here is a key result that relates the rank of complex Laplacian to a graphical condition, just like the one we had for standard Laplacian. But here the rank is not an equality condition, is a lower bound by n-2 if the graph contains a spanning 2 tree. A spanning 2 tree is a subgraph with 2 roots, and all the other nodes can still be reachable from one of the 2 roots, even if we remove an arbitrary node in the graph. In this example, nodes 1 and 2 are the 2 roots, and let's say we take node 4 as an example. If we remove node 3, node 4 can still be reached from node 2 via node 5. And we can also try to remove node 5, then node 4 can still be reached from root 1 via node 3. In fact, it can be verified that no matter which node we remove, node 4 is always reachable from one of the 2 roots. And this holds for other nodes too. So this graph contains a spanning 2 tree. We are going to introduce how this key result for complex Laplacian can be used to establish what's called a similar formation for single integrator type multi-agent systems on two-dimensional space. For that purpose, we are going to represent the 2D space as the complex plane. So the state and the control, xi, ui, are complex numbers. And for formation control, we need to impose a target configuration, which is the desired shape that we want these agents to form. For example, for 5 agents, let's say our desired shape is a regular pentagon, then the simplest way to specify this target configuration vector is to select 5 points uniformly on the unit circle. So we have this one here. Then the similar formation control problem is to design distributed control UI such that it doesn't matter where the agents start, they convert to a formation that can be obtained from the target configuration through some translation, some rotation, and some scaling. And this similar formation can be expressed as a complex linear combination of 2 vectors. The first vector is the vector of all ones that we have already seen in the consensus case. And the second vector is the vector of the target configuration. The coefficient c before the 1 vector represents the translation, and the coefficient c prime before the target configuration vector, if we write it in the polar coordinate, we can see that the c prime represents both the scaling and the rotation that apply to the target configuration. Here note that if the c prime is 0, then we are back to the case of consensus. So for any interesting formation control problem, we will assume that c prime is not 0. Now we can write this set of all possible similar formations by defining this set with the definition we just introduced. Namely, we can write any similar formation as a complex linear combination of two vectors. And we denote this as the set script S of Cassie. With this, we can restate the similar formation control problem as requiring the state to convert to a point in this set. Any point in the set is a similar formation. For the distributed control UI, we are going to use the similar form as we have introduced before in part 1 for the consensus problem, but here with two notable differences. The first difference is this weight Aij. Here, Aij is a non-zero complex number that should satisfy this linear constraint, which involves the relative positions of the agents in the target configuration. Why do we want to do this? Well, if this linear constraint is satisfied, then the weights Aij encode the target configuration in the sense that if we stack all these constraints together, we have this aggregate equation L times C equals 0. Here L is going to be our complex Laplacian, and that equation means that the target configuration vector lies in the kernel of the complex Laplacian matrix. And that's what we want to do, because we will use the strategy like before of driving the state to convert to the kernel of the complex Laplacian. And if the kernel contains the target configuration, or indeed the affine formation to the target configuration, then we are done. The second difference is the addition of this epsilon I. We add this epsilon I in order to ensure stability of the overall system. Why do we need it? Well, as we will see, unlike in part 1, for standard Laplacian, the eigenvalues can be characterized, can be determined using the Gershgorn disks. The eigenvalues of the complex Laplacian are not so well behaved. They can actually be anywhere on the complex plane. So in fact, we have a stabilization problem, and these epsilon i's are brought in to do that job of stabilization. Now let's plug this UI into the dynamics equation and stack these equations together. We get this compact differential equation, x dot equals minus E times L times x. Here we have this E, which is a diagonal matrix with the diagonal entries being these epsilons. And L is the complex Laplacian matrix. And importantly, from these constraints, we have L times C is equal to 0. Namely, C lies in the kernel of the complex Laplacian. We know there's another vector at least lies in the kernel of the complex Laplacian. That is the one vector, because for any Laplacian matrices, their row sum is 0. So that means that there are at least two vectors lie inside the kernel of the Laplacian, the complex Laplacian matrix. And if we compare that with the set of all similar formations, we conclude that the kernel of the complex Laplacian at least contains the set of all similar formations. And the rank of the complex Laplacian can be no more than n-2, because its kernel contains at least now two vectors, 1 and C. So its kernel is at least two-dimensional. That makes the rank at most n-2. At this point, let's bring in the key assumption that the graph G contains a spanning two-tree, because that we know implies the rank of the complex Laplacian is at least n-2. That leaves only one possibility, namely the rank of the complex Laplacian is exactly n-2. So the kernel of the complex Laplacian is exactly two-dimensional. And that means that the kernel of the complex Laplacian is exactly the set of all similar formations. And that's exactly what we want, because with this equality, we feel safe to drive the state toward the kernel of the complex Laplacian, because anywhere in the kernel, it's a similar formation, and that's what we want. So for the entire system, if we can design this diagonal matrix E such that the n-2 non-zero eigenvalues of minus EL are stable, then we know that the state will converge to the kernel of minus E times L. Because the epsilons are non-zero complex numbers, so the E matrix must be invertible. That means the kernel of minus EL is the same as the kernel of L, which is the same as the set of all similar formations. So the state will convert to a similar formation to the imposed target configuration. Now, at this point, we have these two technical issues in our way still to be resolved. The first one is, can we and how can we design these complex weights, non-zero complex weights, Aij, to satisfy these linear constraints so as to encode the target configuration into the kernel of the complex Laplacian? And number two, can we actually design, and how can we design this invertible diagonal matrix E to stabilize the overall system, namely to make the n-2 non-zero eigenvalues of minus EL stable, having negative real parts. Very neatly, both problems can be resolved under exactly the same two conditions. First one is that the graph G contains a spanning two tree. Well, we need this condition anyway. Already we have imposed this condition. And the second one requires that the target configuration is generic on two-dimensional space. For two-dimensional space, being generic means that there are no 3 points on the same line, and there are no 3 lines going through the same point. So those are the two conditions that we need to resolve these two final technical roadblocks before we derive our final conclusion. Let's now illustrate both of these points by example. Here, let's consider node 3. It has two neighbors, 1 and 2, and these happen to be the two roots in the graph. So the linear constraint that node 3 has to satisfy is this one. And if we write the two weights to be designed, A31 and A32, in polar coordinates, it's not hard to see that all we need to do is to rotate and scale these two, this one and this one, these two complex numbers, so that they have exactly the same length, but pointing exactly the opposite directions, so that they can cancel out. And with two neighbors, obviously this is doable. And finally, we just set the diagonal entry of the complex Laplacian A33 to make the row sum, the third row, to be 0. And we can do the same for the rest of the nodes. The resulting complex Laplacian is this one. And we can verify that both the one vector and the Cassey vector, in this case is the regular pentagon, both lie in the kernel of this designed or computed complex Laplacian. However, the eigenvalues of minus L contains a unstable eigenvalue, the last one marked in red. So we need to stabilize this minus L by designing an invertible diagonal matrix E. I'm not going to cover the detailed steps of designing this E, but there are algorithms available to do this job, and one solution E is this one, and we can verify that it does the job. So with this E, we have the eigenvalues of minus E times L being the following. There are exactly two eigenvalues 0, and the other 3 eigenvalues are stable. So with this pattern of eigenvalues, we should expect similar formation. And indeed, we have it. Starting from a given initial condition, the agents convert to a regular five-gon or pentagon shape. And here is our solution to the similar formation control problem. Using this form of distributed control UI with the stabilizing epsilons and the complex weights Aij, we can resolve the similar formation control problem for multi-agent systems under two conditions. One, the graph G contains a span into tree. Two, the target configuration C is generic. A very appealing feature of similar formation control is that we can manipulate the entire formation by simply controlling the two roots. For example, if we change the relative positions of these two roots, then we can rotate the whole formation. If we move both roots, we can translate the whole formation. If we move the two roots closer to one another, we can scale down the formation. We can do the opposite by moving them apart. So very convenient to manipulate the entire formation. Doesn't matter how many agents are there, as long as we manipulate the two roots, we can do three basic transformations for the formation: the rotation, translation, and scaling. Talking about scaling, can we do such scalings? Namely, can we scale the whole formation with different ratios along different axes as displayed on the two graphs on the right? Well, why we might want to do such thing? Well, in the environment, there might be such obstacles that create a tunnel, and being able to scale the formation with different ratios on different axes can enable us to efficiently navigate the whole formation through such tunnels created by obstacles. However, such different scalings cannot be done in similar formations because there's only a single scaling ratio in similar formations. And to be able to scale with different ratios along different axes, we will need a different way of controlling the formation. And that is what's called a fine formation, achievable using signed Laplacians. And that's going to be covered in our next part, the part 3. So here is the end of part 2. So see you next time.